Hello, this is Ray Dempsey and I'm here to talk to you about graphing quadratic functions using Vertex form. Quadratic functions have the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is non-zero. The graphs of functions of this form are always parabolas. Let's look at a few examples. Starting with a visual approach, let's take note of some qualities that each parabola has. First, we see that each parabola is U-shaped. Now, some are wider and others are narrower, but there's still a general U-shape to each one. Second, parabolas open upward or downward. Since we'll be using x as our independent variable, we won't see parabolas that open to the left or to the right. Next, each parabola has a vertex. The vertex of a parabola is like a turning point where the graph of the parabola sort of changes direction. For parabolas that open upward, the vertex is the point where the graph goes from being a decreasing function to being an increasing function. It's also the minimum point on these graphs. Similarly, for parabolas that open downward, the vertex is the point where the graph goes from being an increasing function to being a decreasing function. It's also the maximum point on these graphs. And lastly, each parabola has an axis of symmetry. This is the vertical line that goes through the vertex that splits the parabola right down the middle. Each part of the parabola is a mirror reflection of the other over the axis of symmetry. Each axis of symmetry will have an equation of the form x equals h, where h is the x-coordinate of the vertex. We want to develop our instinct about graphing quadratic functions with these properties in mind. Let's start graphing quadratic functions first by graphing the most basic quadratic function, f of x equals x squared, by plotting points. We see its vertex is located at 0, 0, and its axis of symmetry is the line x equals 0. Let's compare it to the graph of the function g of x equals 1/10 x squared. Notice that this parabola is wider than the parabola pertaining to the graph of x squared. In fact, the closer to 0 the x squared coefficient a becomes, the wider the parabola will be. Similarly, the larger the absolute value of a becomes, the narrower the parabola will be. If this coefficient is positive, the parabola will open upward. If this coefficient is negative, the parabola will open downward. Changing the sign of a reflects the function over the x-axis. Note that changing this coefficient does not affect the position of the vertex or the axis of symmetry of the parabola. What we want to do now is we want to learn about shifting the graphs of our parabolas to the left or to the right and to identify qualities of quadratic functions with this concept in mind. In a quadratic function, if we replace x with x minus h, this will shift the parabola to the right h units. For example, if we wanted to shift the quadratic function f of x equals x squared to the right 4 units, we would replace x with x minus 4. In this example, h equals 4. Notice that this shifted the vertex of the parabola from 0, 0 to 4, 0. Again, if we wanted to shift the quadratic function f of x equals 1/3 x squared to the left 5 units, think of it as shifting the parabola to the right negative 5 units. So we would replace x with x minus a negative 5, or x plus 5. In this example, h equals negative 5. Remember that h represents how many units to the right the parabola was shifted. Notice that this shifted the vertex of the parabola from 0, 0 to negative 5, 0. So in general, what we just learned is now we can easily graph functions of the form g of x equals a x minus h squared, because all we're doing is simply graphing the function f of x equals ax squared and shifting it to the left or right h units depending on whether h is positive or negative. We see the vertex will be the point h0, and since the axis of symmetry is always the vertical line passing through the vertex, the axis of symmetry will be x equals h. Another thing that's convenient is we don't need to graph functions of this form to identify their important qualities. Examining the function g of x equals negative 0.5 x minus 2 squared without graphing, we see that it's of the form ax minus h squared. And since we see that h is equal to 2, we know it will look just like the function f of x equals negative 0.5 x squared, but shifted to the right 2 units. We know its vertex must be located at the point 2, 0 because we took a function that has its vertex at 0, 0 and shifted it to the right 2 units. Its axis of symmetry will be x equals 2. And lastly, since a is negative, the parabola opens downward, so it will obtain its maximum value at the vertex. What we want to do now is we want to learn about shifting the graphs of our parabolas up or down and to identify qualities of quadratic functions with this concept in mind. In a quadratic function, if we add k to the end of the function, this will shift the parabola up k units. For example, if we wanted to shift the quadratic function f of x equals negative 2/9 x squared up 7 units, we would add 7 to the end of the function. In this example, k equals 7. Notice that this shifted the vertex of the parabola from 0, 0 to 0, 7. Again, if we wanted to shift the quadratic function f of x equals 1/8 x plus 3 squared down 6 units, think of it as shifting the parabola up negative 6 units. So we would add negative 6 to the end of the function, which is the same as subtracting 6. In this example, k equals negative 6. Remember that k represents how many units up the parabola was shifted. Notice that this shifted the vertex of the parabola from negative 3, 0 to negative 3, negative 6. So in general, when we graph functions of the form g of x equals a x minus h squared plus k, we're just graphing the function f of x equals ax squared and shifting it to left or right h units depending on whether h is positive or negative, and up or down k units depending on whether k is positive or negative. We see the vertex will be the point hk, and since shifting a parabola up or down doesn't affect the axis of symmetry, like before, the axis of symmetry will be x equals h. And this, ladies and gentlemen, g of x equals a x minus h squared plus k, is what we call the vertex form of a quadratic function. We call it vertex form because we can easily identify the location of the vertex of the parabola without graphing. Examining the function g of x equals 3x plus 1 squared minus 8 without graphing, we see that it's in vertex form. Since we see that h equals negative 1 and k equals negative 8, we know that it will look just like the function f of x equals 3x squared, but shifted to the left 1 unit and down 8 units. We know its vertex must be located at the point negative 1, negative 8, because the vertex is always located at hk. Its axis of symmetry will then be x equals negative 1. And lastly, since a is positive, the parabola opens upward, so it will obtain its minimum value at the vertex. This is great when we're asked to graph a quadratic function in vertex form, but what if our function's in standard form? It turns out that in a few quick steps, every quadratic function can be converted to vertex form. Given a quadratic function in standard form, we want to convert it to vertex form by a process called completing the square. First, we factor the coefficient of the x squared term out of the first two terms. Next, we complete the square on the inside by adding and subtracting the value that completes the square. We find this value by taking the coefficient of the x term, dividing it by 2, then squaring it. Then, we split the last inside term off so what's left over on the inside is a perfect square trinomial. Then finally, we factor our perfect square and simplify. Now that we've converted it to vertex form, we can easily see that the vertex is located at 3, negative 8. This is when the axis of symmetry can come in handy for graphing. We can compute the functional values of points on one side of the axis of symmetry, and since the parabola is reflected over this line, we can plot these points without further computation. Converting the general quadratic function into vertex form by completing the square, we see the vertex is located at the point negative b over 2a, 4ac minus b squared over 4a, which is more often written as negative b over 2a, f of negative b over 2a. Hopefully this can get you rolling in your quest to graph quadratic functions. This is Ray Dempsey reminding you that math is simple. Well, once you get it.